All right, class. So we're going to switch gears today. And after talking about statistics, for the first week, we now switch over to probability. Probability is the study of randomness. And it can answer all sorts of interesting questions, like what are the outcomes of flipping a coin or rolling a die, or what are the chances it's going to rain today, or that you get an A in this course, or maybe that your crush says yes when you ask her out, or how about in the NFL, or sorry, in sports in general, there's lots of interesting gambles or wagers. In fact, you can gamble on anything. They're taking bets for the who's going to win the Academy Awards right now. And apparently, it was gambling that was actually the impetus for much of the original study of the foundations of probability. Yeah, it was people trying to get an edge, winning at the casino. And there are all sorts of stories, allegories of smart people that knew something about probability that were able to take those skills to the casino and win big bucks. Maybe you've even heard of the movie 21 about MIT students who made millions in Vegas counting cards and blackjack. And there's a whole lot of stories like that. As for myself, I put down 4 separate bets this past weekend on the NFL playoffs, and I needed all 4 of them. I needed to win on all 4 in order to get paid. So if you imagine that, let's say each one there was only a 50% probability of me getting it right, if you work out the odds, and we're going to go over this in the next couple days, that would mean I only had a 1 in 16 chance of winning that bet. But if I did, then a $10 bet would have won me $160. And I did. Yeah, I actually did win that bet. Thank you. I was surprised too. That was the first time that happened. And actually the numbers were a little bit less because the casinos take their percentage. But so we're going to talk about that stuff, learn about that stuff today. That's my little motivation. Let's start off with the basics, the foundations of probability theory. So let's say that you are trying to model a procedure or an experiment. There are 3 relevant elements to this. So to model a procedure or experiment, first you need to set up what are the possible outcomes. And the set of all of these is called the sample space. Okay, so there's 3 components. The first component is the sample space, which is the set of outcomes. The second component we're going to call events. And events, they could be single outcomes, but more generally, they are collections of outcomes. And when you do an experiment, an event either occurs or does not occur, depending on whether the outcome of the experiment included outcomes that were in this event. And then probability is assigning numbers to the different events. That is to say, the probability of the event. So here's an example. Start off with dice. So if you roll a die, then the set of possible outcomes is the sample space, which is either 1, 2, 3, 4, 5, or 6. So the sample space would be 1, 2, 3, 4, 5, or 6. And so you could have an event with the event being that you roll a 1, okay, or a 5 or a 6, or you could have an event that you roll an odd number, for example. So that's a collection of specific outcomes. So here's some examples of events. Let's say A is the event that you get an odd number. So either a 1, a 3, or a 5. And B is the event that you, say, roll a 5 or a 6. And C is just specifically that you're looking to get a 6. Okay? So we can now assign probabilities to these different events. This is 1, this is 2. The probabilities, what's the probability that we get an odd number on the roll? 1/2, or 3 out of 6, because there are 3 events that would make that, there are 3 outcomes that would make that event true. Similarly, there are 2 outcomes that would make the event be true. That is to say, you either roll a 5 or a 6. And there's only 1 that makes C true. But this is based, these numbers are based on the assumption that it's a fair die. In other words, each one of these outcomes is equally likely. This isn't always the case, though. But it is here, and it's why we were able to assign probabilities to those events. Here's some more terminology. The complement of an event A, which is denoted A with a superscript C, is the event that A does not happen. So to use the dice example, if A was the event that we roll an odd, then a complement would be the event that we roll an even number, which is 2, 4, or 6. And B was that we got a 5 or a 6. So B complement would be that we either got a 1, 2, a 3, or a 4. All right, any one of those would mean B was false. We say that 2 events are disjoint, or mutually exclusive when one implies that the other cannot happen, or they can't both happen. So let's see, in my dice example, look at these events. Are any of those disjoint? A and C are disjoint there. Okay, here's some rules for finding probability. First, the probability of an event is always a number between 0 and 1, possibly including 0 and or 1. If the probability is 0, that means the event cannot happen. If the probability is 1, it means the event will definitely happen. And since it's a number between 0 and 1, we often will express it as a percent. So if I said there's a 30% chance that you get an A in this class, that means the probability that you get an A is 0.3. Because either something happens or it doesn't, the probability of the complement of an event is always 1 minus the probability of an event. So there's a 100% chance that something happens, is what this says. Okay, back to the NFL. Do we have any Chiefs fans in the room? Cool. Okay, one Chiefs fan. Two. Okay. Tentative Chiefs fan. How about Green Bay fans? Yeah, no, that's a guy. I like Green Bay. Yeah. Okay. Titans. No one's going to be for the Titans. Okay, and now I'm going to expect some here. How about San Francisco? That's what I thought. Yeah, there's always a few from the Bay. So San Francisco is currently estimated. It has the best odds to win the Super Bowl this season. San Francisco, if you look at the odds makers, has about a 35% chance of winning the Super Bowl. So the San Francisco 49ers have a 35% chance. What are their colors? It's red and gold, right? Let me see. Okay, so the 49ers have a 35% chance. What is the probability of the event that they do not win the Super Bowl? Is 65. Now, if you have two events that are disjoint, then we have the following. Oh, and just in case anyone asks, this ampersand means and. A and B are disjoint, then the probability that one or the other happens, including the possibility that they both happen, this is the inclusive or, is simply the sum of the two probabilities. So the Green Bay Packers have, what is theirs, a 20% chance of winning. Now, only one team wins the Super Bowl. So what's the probability that either the Packers or the 49ers win the Super Bowl? 55, good. But what if you want to take, oh, oops, I want to do this in black. The probability of one event or another, but they aren't necessarily disjoint. So in general, in fact, there's a name for this. This is the addition rule. The addition rule states that the probability of A or B, it's the probability of A plus the probability of B minus the probability that they both occur. If the two events are disjoint, then the addition rule just reduces to rule 3 up here. But this is a bit more general. The reason we have to subtract off this last term is to avoid double counting it, right? Because like the event that A and B occurs means they both occur. So, well, we already counted that when we counted A. We don't want to counting B then double counts it, so that's why we have to subtract it off. This is kind of most easily understood if you look at a Venn diagram. So here's a Venn diagram for this to sort of illustrate the addition rule. So this big box will be the set of all possible outcomes. So let's make this one A, and let's color it blue. And let's make this one B and color it yellow. Then the region where they overlap there, that's the event that A and B occur. I.e., for those of you that are familiar with the notation, that's A intersected with B. And is the same as intersection. On the other hand, the collection of all of them together is A or B, i.e. the union of A and B. So the Venn diagram makes the addition rule a bit more clear, right? Why we have to subtract off the intersection, the green part, because we don't want to double count it. Here's an example. How about back to die? Back to rolling dice. So if A is 1, 3, 5, and B is still the same as it was. B is 5, 6. C is well, I'm not going to use C, but I'll write it anyway. Okay, so what's the probability that A or B happens? Well, let's write out what is A or B. It means you're in A or you're in B, either one. So that's all the elements that are in A or in B, which includes a 1, a 3, a 5, and a 6. Okay, so the probability of A we already computed was 3 out of 6. The probability of B, again, we already saw was 2 out of 6. And you can see from the fact that it has 4 elements that the probability of A or B will be 4 out of 6, which is exactly probability of A plus probability of B minus, oh, wait, I still need to calculate one, which is A and B, since the only thing that's both in A and B is the element 5. So probability of A and B is 1 out of 6. Cool. Okay, so the formula seems to work, seems to hold. Works in this case. All right, because 3 plus 2 minus 1 is 4. Here's another example. How about if you pick a card at random? From a 52-card deck. What is the probability that it's a, how about a 7 or a heart? So the probability that we get a 7 or a heart will be the probability we get a 7 plus the probability we get a heart minus the probability that it's, well, the 7 of hearts. So let's see. How many 7s are there? There's 4 of them. How many hearts are there? 13. And there's just 1 7 of hearts. And by the way, this comes out to about 0.307. Any questions? Or, okay, here's another example. How about with the class survey data? Okay, so according to the class survey data, which, okay, so according to the class survey data, 66% of the class survey respondents were female. Which makes me feel that like more women were responding than men. That seems kind of high, right? Like 2/3 of the class is female. I feel like a lot of the dudes didn't respond. You know? So what? Thank you. I appreciate it. Yeah, to those of you that did, I appreciate it. So it kind of might skew my data a little bit. We didn't read chapter 10 in the textbook, but you should read it. And in chapter 10, they discuss voluntary response bias when you do a survey. So this would be an example of that. When I teach this class again in the spring, I think I'm going to repeat the class survey, but I'm going to do it in class and tell everyone to do it so that we don't have this sort of bias. So I might talk about the class when really I'm talking about the class survey respondents. Okay, so according to the data, 67% of the class survey respondents is female, and 55% are single. Interesting. Okay. 37% are both. So what is the probability that a randomly selected respondent or student is, okay, let's do, how about female but not single? Or how about neither female nor single? Now, it might be easier just to write out a Venn diagram for this, but first let me try doing it using the equations, because, so here's the answer. So for 1, if you're a female, then you are either single or you're not single. Those are disjoint sets, the single females and the not single females. And together, they make up all the females. So if, let's just call F be the female respondents, how about S be the single respondents, then the probability that the respondent is female is, by the addition rule, the probability that the respondent is female and single plus the probability that she is female and not single. I.e., what are our numbers? 0.66 is equal to, female and single was 0.37. So probability of being female and not single was 0.66 minus 0.37, or 29%. Pick a random student from the class that responded. There's a 29% that she is female and not single. How about for neither female nor single? Notice that not female, sorry, let me write it like this. The probability that you are not female and not S, that's the complement of the probability that you're either female or single. Single or female complement. So it's 1 minus the probability that you are single or female. Well, we can use the addition rule to find the probability of single or female, because that's the probability of being single plus the probability of being female minus the probability of both. So, okay, single was single was 55. Single was 66. Both were 37, and this adds up to 84. So probability of being not female and not single is 1 minus 0.84, or 0.16. And like I said, it's actually often a lot easier just to draw the freaking Venn diagram here, where, you know, like this one is 66. This one is, what is it, 55. This one right here is 37. And so forth. I'll let you fill in the details of the diagram if you want. Oh, all right. I'm doing okay. Any questions? On to conditional probability. Like this one means the complement, like the event that this does not happen. It's the opposite. So I'm saying, like, if you are not female and you're not single, that is the opposite of being either single or female, right? This is the statement that single or female did not happen. So like, for example, let's shade in that region, how about? What does here? Not female and not single, which is the same as single or female complement, is what region of the Venn diagram is single or female complement? Outside of both balls. So that's this region. On the other hand, let's shade in like here. How about female and not single? Let's see. So that would mean you're inside the female one, but outside the single one. So that is this right here. Yeah. So let's see, I have some graphs. It takes a long time to like prepare examples for this lecture using the class data because it's hard to find what the perfect example is, and inevitably I don't have time to check to find the perfect freaking example to exactly illustrate the point. But here's some data we got from the class survey. So the first one, okay, unrelated to statistics, you might notice like if you're 18 years old and single, don't worry, right? Like as you get older, more and more of you are ending up in relationships. At first, almost the majority of students at 18 were single. Eventually, by 21. So you're probably going to leave college with a boyfriend or girlfriend is the point of that graph. And, in fact, so if I asked you, or if I asked the class, like, all right, what are the chances that you're single? Or the chances that you're in a relationship? Well, I could just crunch the numbers for the whole class. How many singles are there? How many relationships are there? And that would give me that. But what if I gave additional information in the question? And I said, what are the chances that you're single given that I know that you're 21? It would be a lot less, right? Yeah, so it seems like once you hit 21, there's a lot greater of a chance that you're in a relationship. This is an example of conditional probability. So let's see. What example should I use? Got a dice example, but I feel like the relationship stuff is maybe a bit more fun and interesting. Except I haven't found the perfect stat to use. Okay, let's use this chart with sex and relationship status. How about? So from this one here, this is not all the respondents. This is just those that said they were either single or in a relationship. So there were a total I'm looking now at this graph. There's a total of 130 students represented here. So let's just look at the 130 students that are either male or female and either single or in a relationship. And the number of males in this group is 45. The number of students who said they were in a relationship, let's call that R, is 48. Does the probability that you are in a relationship seem to change with whether you're a male or a female? It does. So, which one is more likely to be single, the women or the men? Who's more likely to be single? From this graph, the women have a lot bigger of a single column than relationship column. Now, there is also the other column, which I'm not displaying here, and maybe someone wrote other just because someone was going to be mad at them if they wrote single. It's kind of a funny thought. Okay, so I want to ask the probability. Here, okay, where's my numbers? There are 18 males that are in a relationship. What's the probability that, how about let's ask, if you meet someone who's in a relationship, what's the probability that they are male? Okay, so, well, we can count it up. There are, of the people that are in a relationship, so that would mean of this column and this column, that was 48 people total, right? Just what I said here. So of those 48, 18 of them were males. So there's an 18 out of 48 chance that you're a male given that you're in a relationship. Notice that I could write this as 18 over 130 divided by 48 over 130, which, hey, this top number, what's this? That's the probability that you're a male in a relationship. And the bottom number, that's the probability that you're in a relationship. So this whole thing is just the probability you're male and in a relationship divided by the probability that you're in a relationship. So here, let me go back. Here, I'm going to make this easy on you. All right, I'm going to switch screens, but I'm going to paste it on the other screen. So this is what leads us to the conditional probability formula. Here's the definition. If A and B are events with the probability of B strictly being positive, you can't do a conditional probability when there's no chance of, like, what's the probability you're single if you're a unicorn? Doesn't make sense to ask that question. But if one of them has positive probability, then we define the conditional probability of A given B to be P of A, and we write a bar. That means conditional probability, and the formula is probability of A and B divided by the probability of B. In other words, if you look at the Venn diagram, let's see, like in the Venn diagram here, it's like if you know that you're in the blue, what are the chances you're in the green? That's the conditional probability. And that is it for, you guys are leaving soon, but actually I'm done, so it's okay. Just for, in general, I don't like that, but yeah, we're done. We can end a little bit early.